All right. It was an absolute pleasure to work with Ankita this summer. She actually helped my group out a lot. She compared some new models of dwarf galaxies that we've developed with observations of the dwarf satellites around Andromeda. And she did an absolutely spectacular job. And I think you're going to really enjoy the talk that she put together.
All right. Thanks, Mia. I'm going to share my screen now. Comparison of Andromeda dwarfs with simulated models. Here, we are looking at a backdrop about 4.6 billion light years away. First, why do we study dwarf galaxies? Dwarf galaxies are smaller galaxies containing up to a few billion stars, thought to be formed by the gravitational forces in the early stages of creation of their larger counterparts. They are, in fact, the most common kind of galaxy in the universe. What is so special about them? Well, they're quite sensitive to changes in their external environment as well as their internal environment. They are prone to stripping of their gas and stars in response to changes in their neighborhood. They also tend to have low metallicities, like that of the earliest galaxies. Therefore, their study helps us understand the evolution of galaxies, dark matter halos, and the universe. Over the past 20 years, the number of dwarfs discovered around Andromeda and Milky Way has doubled. By the way, we're looking at a stunning image of I Zwicky 18, a dwarf galaxy about 59 million light years away. Coming much closer, Andromeda is a large spiral galaxy. It's our largest galactic neighbor, about 2.5 million light years away. It is also known by its catalog number M31. This galaxy spans about 260,000 light years across. Milky Way and Andromeda are part of a group of over 50 galaxies called the local group. The local group spans a volume of about 10 million light years in diameter. In this depiction of the local group, we see Milky Way and Andromeda. Triangulum galaxy, also known as M33, is another prominent member. The rest of the group is composed of several dwarf galaxies. The local group is constantly changing due to galaxy interactions. Coming to our project, we have compared key properties of Andromeda dwarfs with that of simulated ones using semi-analytical models. We wanted to see if the observable properties of Andromeda dwarfs can be reproduced in model datasets. We've added Milky Way dwarfs as well for reference, since our model was based on the Milky Way analog. Our observational study included 80 dwarf galaxies, with 65 model dwarfs. The properties we compared were luminosity, half-light radius, velocity dispersion, mass enclosed, mass to light ratios, and metallicity. Luminosity is the energy emitted by a celestial object. We have looked into the visible light luminosity for this study. Luminosity is measured in solar luminosities. Luminosity functions tell us about the relative number of galaxies within various luminosity intervals. We've plotted the cumulative luminosity functions of the observed Andromeda and Milky Way dwarfs and the model dwarfs. The cumulative luminosity function is a cumulative distribution of the number of galaxies with luminosity greater than a given luminosity. Here, the light blue line refers to the luminosity function of Milky Way dwarfs, the dark blue line is that of Andromeda dwarfs, and the yellow line is that of the model dwarfs. The luminosity function of the model mostly matches that of Milky Way dwarfs, since the Galacticus model was based on a Milky Way dark matter profile. We see that most of the Andromeda dwarfs have reported luminosities over 10 to the 5th solar luminosities. This is expected, since faint dwarfs of Andromeda are unlikely to be recorded in observations due to their distances. Andromeda, being massive, is likely to house many dwarf galaxies when compared to the model, and this is evident in the graph. Halflight radius. This is the radius that contains half of a galaxy's light. We're unable to make out well-defined boundaries of galaxies. So, we use half-light radius as a measure of definable size of galaxies. This is the scatter plot of the half-light radius against luminosity. Half-light radii are measured in parsecs. A parsec is a little over 3 light years. Again, the dark blue dots denote the Andromeda dwarfs, the light blue are the Milky Way dwarfs, and the yellow are the model ones. We see that the model overestimates the half-light radius for fainter dwarfs. This is due to the uncertainty in the determination of the dark matter profile of low-mass halos that host these dwarfs. We can also see a direct relation between the half-light radius and the luminosity. Velocity dispersion is the statistical dispersion of stellar velocities, and it tells us about the strength of the gravitational potential of the galaxy. Velocity dispersion is measured in kilometers per second and is denoted by sigma. In the histogram, we see that velocity dispersions of the three datasets mostly match. We have shown only those observations with known velocity dispersion. The maximum observed velocity dispersion was that of an Andromeda dwarf, and it was 92 kilometers per second. The model data presented a maximum sigma of about 40 kilometers per second. This slide shows the scatter plot of velocity dispersion against mass enclosed. They have a direct relation, with heavier dwarfs having a greater velocity dispersion. The scatter plot of velocity dispersion against luminosity also shows a slight upward trend, with more luminous dwarfs having a relatively higher sigma. Here, we've calculated the mass enclosed within the half-light radius of the galaxy. It is calculated from the velocity dispersion and the half-light radius using the formula mass enclosed equals 3 times sigma squared times half-light radius divided by g. The masses are expressed in solar masses. In this histogram, we see that the enclosed masses of the datasets match well. A few of the Andromeda dwarfs had to be masked as their half-light radius was unknown. Mass to light ratio, given by mass enclosed divided by luminosity, helps us estimate the relative proportions of stellar mass and dark matter. Here we have a scatter plot of the mass to light ratios against luminosity. We see that the ratios are higher for the model dwarfs as denoted by the yellow dots. This is due to the over-prediction of half-light radii by the Galacticus model. However, the maximum observed mass-to-light ratio was 521. This gives us an idea of the amount of dark matter present. Next, we have compared the metallicity of dwarf galaxies in this scatter plot. All elements heavier than helium are referred to as metals in astronomy. Metallicity is the fraction of the galactic mass composed of metals. Metallicity is influenced by enriched raw materials from generations of stars and winds that may cause metal loss or gain. In general, the metallicity of a dwarf galaxy is usually low, since the weak gravitational potential is unable to stop metal loss in winds. The metallicity, or the iron abundance, is compared on a logarithmic scale in units of solar value. So, a value of 0 would mean an iron abundance the same as that of our sun. A value of -1 would mean there is 1/10 the iron abundance as our sun. The metallicity of Andromeda dwarfs, as denoted by dark blue dots, range from -2.33 to -0.25. This would mean the iron abundance in these dwarfs range from 0.0046 to 0.56 times that of our sun. The Milky Way dwarfs, the light blue dots, show metallicity from -2.76 to -0.4. The model dwarfs, which are the yellow dots, show a minimum metallicity of -2.35 and a max of -0.74. The metallicity of the model matches well with the observed data. Most of the observable parameters of Milky Way and Andromeda dwarfs were reproduced close enough in the Galacticus model. The discrepancy in the half-light radii was due to the poor resolution of the dark matter profile of low-mass halos in the model. Keeping this in mind, the Galacticus model can be used for further comparisons beyond our local group to analyze star formations in low-mass systems and the evolution of dwarf galaxies. Immense thanks to Dr. Mia Vogel, my SME, for expert guidance, Dr. Lynn Kaminsky for valuable inputs, and Dr. Ariana Riccio for coordinating the internship and for being my boss.